Okay, so today we're going to be looking at solutions, which is our 15th chapter. Now, when we talk about solutions, we're going to introduce at first just some terminology, and then what we're going to do is actually look at what actual factors we have that's attributing to our solutions. Then we have some units, and then we're going to talk about some math we can do with those units. All right, so first terminology is describing the components of a solution as being the solute and the solvent. Now, there are allowed to be more than one solutes. Those are the things dissolved in the solution. So, like if we're talking about sodium chloride in a solution, salt is the solute, and then water would be the solvent, which is the other component in there. So those are our two main components. The solvent is going to be the stuff that is in the large amount, or the stuff that actually retains its phase, so like the water and the salt water. Now, what's interesting, it doesn't actually have to be always the lesser amount and more amount, like it says here, because interestingly, something that you guys probably are aware of is there is something called isopropyl alcohol. We use it as a disinfectant in our homes. Well, if you go into most stores and look at it, you might find as much as 70% isopropyl. You might find 30%. Now, those percents really are talking about the comparison of the isopropyl alcohol and water. And if we are talking about that 30%, that does mean that there's roughly 30 grams of isopropyl alcohol and 70 grams of water. So water would be the solvent there. But 70% means there's actually more isopropyl alcohol. Yet, even though it is true that there's more isopropyl alcohol, it's not necessarily right to say the isopropyl alcohol is the solvent. Being reporting that 70%, they're actually saying that the solute is the isopropyl alcohol. And the rest, the water, which only makes up 30% in this case, is the solvent. So this line is not always true, that always in lesser amounts part. All right, next one that we're going to point out is that at least at first in our solutions, more often than not, our solvent is actually water. And anytime we've had in a chemical formula, a balanced equation, that little AQ in there, aqueous, that actually guarantees this means water. So if you see aqueous, it just means that particular substance is dissolved in water. Now, something else we're going to add to this terminology is when we're talking about a solution, we're going to point out that the solution should be homogeneous. That basically just means it looks the same throughout. Gatorade's a good example of this. Once you've actually mixed up the powder and water, it looks uniform throughout, and it's going to be that way until we actually do something crazy and try to separate those two. Those actually are very difficult to separate, but you theoretically could boil off the water. It wouldn't necessarily leave the powder in a usable form because Gatorade actually has sugar in it, and that sugar will probably caramelize if you were to heat it up. Alright, next thing we're going to talk about is why is water our aqueous solution to go to? It's really because it's very versatile, it's very common, but it does have some very unique properties. It has a very high boiling point and melting point compared to other things at the same molecular weight. Has a high heat of vaporization, can handle a lot of temperature before it starts to change its temperature. And there's quite a few things that dissolve in it. It's what we call a universal solvent because you can dissolve a lot. Alright, turns out there are other solutions that don't involve water. There's other solutions that don't involve liquids. So solutions can be made out of different phases as well. Obviously we can dissolve solids into water and gases into water, but we can also do solids into solids. Those are typically called alloys, but they are kind of like solutions. Now, my picture over here is showing how we go about making brass, which is a mixture of copper and zinc. Turns out copper, which is a relatively easy metal to purify, even a decent wood-based smelting oven could actually get hot enough to purify copper. But copper is not a very strong metal in the sense that it bends quite easily. If you were to make a sword out of copper, it would bend too easy to be a useful weapon. So they make alloys by mixing with various different things to get different properties. Brass is one used to actually make musical instruments. It's got a nice little tone. Bronze was the one that we typically see swords and such made out of. And then down below we have carbon steel. Now this is an interesting one. The little dots there are carbons. That is how we view it happens, in the sense that you get it up to the right temperature and the carbon embeds. Now carbon, in this case graphite, when you do that, the metal actually looks darker. It actually, carbide steel or carbon steel is very dark compared to regular steel, but it does make it very, very strong. Alright, other solutions that don't necessarily involve water. We have the air around us is a solution. It's a solution mostly of nitrogen and oxygen, but it could be considered a solution. Carbonated soda is a solution. It's just carbon dioxide dissolved into our liquid. And then the other ones are actually back to aqueous solutions. We got seawater, which is salt dissolved into water, and we have antifreeze, or even the isopropyl alcohol we were talking about before, which is a liquid dissolved in a liquid. But for the most part, what we're going to see is the same, is that whatever state the solute should have been at room temperature is what the state of the solution is. Okay. Next little thing we're going to talk about is some more terms that talk about how much solute is dissolved in the solvent. Now, the most you can put on a given substance is what it's called the solubility. Like, for instance, sodium chloride, NaCl, has a maximum solubility. Excuse me. Sodium chloride's solubility is about 360 grams per liter. So 1 liter of water, you can dissolve about 360 grams of sodium chloride. Once you dissolve any more, like if you tried to put 400 grams in there, you'd have about 360 dissolved, and 40 of it would settle at the bottom. And that solubility does change, just for the sake of discussing it. Sodium acetate, another sodium salt, its solubility is going to be listed a little bit different. It's 123, or 1,230 grams per liter. So a heck of a lot more. Alright, now, what's different about that, we don't actually have to always have the maximum in there. Like, for instance, the ocean has a trace amount. Your tears have a trace amount of salt in there. We would consider both those unsaturated solutions. They just have a number that's less than that. You could still add more, and more could go in. And saturated is when you've got to the point where no more can dissolve. Saturated. Now, supersaturated is kind of interesting. Can't really do that too easy with sodium chloride, but sodium acetate is a different story. Turns out if I get sodium acetate water hot, hotter than up to like 100 degrees, that number, that 1200, changes to closer to like 1600. And you can actually dissolve a lot more when the water's hot. Now, what's neat about sodium acetate is if you dissolve more when it's hot and then let the water cool back down, it'll stay in solution. It'll still be a solution, but it's now what we call a supersaturated solution. I have a little video to show what happens to a supersaturated solution if you put a single crystal back in there. So, this solution, sodium acetate, and the person's going to lift up here a micro spatula that has a spot of sodium acetate on it, and then they're going to just drop it into the flask. And the crystal is small enough you can't even really see it in this video. But it's on the end there. And then watch when it hits that surface. This is real time, not sped up or anything. This is exactly what would happen. Essentially, the solution now remembers what its crystal pattern was, or builds off of it. Just repeats what it sees in that crystal. And every bit of that extra sodium acetate precipitates out. And it is fast enough it does it before it even has a chance to fall to the bottom. But if you notice, pretty much all that water is entrapped in that solid. Now, what's neat about this, that got really hot when that happened, and if you warm it up now, well, let it cool back down, and then warm it back up, you can redissolve that in the exact same container. You don't have to do anything to it. It'll just redissolve, and then it could happen again and again and again. You see these as instant hot packs to some degree because they will put that in a little plastic bag. You flip the little discs that gets the crystallization to happen. It gets hot. You use that for your heating pad, and then when you want to use it again, you throw that into some hot water and redissolve the sodium acetate. It's ready to go again. Other supersaturated solutions you've come in contact with, maple syrup. It's actually a supersaturated solution of sugar water. At least that's other additives in there, but the main supersaturated substance is just sugar. Okay. We talked in our last, we've talked before about our intermolecular forces and the ion dipole attractions. That's what's going on when sodium chloride separate and get surrounded by water. That happens because the intermolecular forces between the sodium and chlorine and between the sodium and water and chlorine and water are comparable. We actually use that phrase, like dissolves like. But what we're saying is, since it does dissolve, we are saying that it must have comparable electrostatic or intermolecular forces. And the term we're going to use to describe that is solvated. Solvated just means the ions dissolve. They actually get surrounded by the solvent. All right, and we've got a picture representing what we're talking about at the microscopic scale. So you have your ionic compound, and as it separates out, the positives get surrounded by water and the negatives get surrounded by water. It's just that the orientation of the water varies. Around the positives, the oxygen on the water molecule gets closer. Around the negatives, the hydrogens get closer. All right. And we also talked about different solubility rules in the past, and we talked about how some were always soluble. Well, that's what they're talking about here. It's just a re-summarizing of that. If you notice, we have our nitrates and we have our sulfides, which were some of our two extremes. We said nitrates were pretty much always soluble and sulfides were pretty much never soluble. And that's what they're talking about here. But what we're saying is, as these dissolve, some are always solvated and some are never solvated or unlikely to be solvated. But as long as the electrostatic forces are comparable with the ion and water, they actually dissolve. And the same thing happens with organic molecules or covalent molecules as well. And the one listed in this picture down below is actually methanol. Single carbon with 3 hydrogens and an OH. Turns out that OH allows methanol to hydrogen bond with water. Greatly enhances the solubility. Now, having just OH isn't always enough, because if I add more carbons on this, so instead of just one carbon, I'm going to draw this wonderful molecule. This is called butanol. So it still has an OH on it, and it does make hydrogen bonds, but the other end, that is all nothing but strong carbon nonpolar molecule, that part of the molecule only wants to do London dispersion connections, and it's not compatible with water. Turns out butanol is not as soluble in water as methanol. It's very much more likely to separate out, actually. All right, so how about this? Would we think something like this then would be soluble in water? No, that's actually just a petroleum product right there. That one is actually probably not even found in gasoline. Might be found in diesel, but it's actually probably too high for that. That would probably get broke up into something smaller before it gets used as a oil. That's actually getting to be enough carbons it could end up as asphalt. But if you were to mix that with water, you get that separation. The long nonpolar molecules would separate totally from the water, and you'd get the oil and water not mixing. Yeah. Obviously, we could shake it up, but as soon as you stop shaking it, they would separate back out. Okay, so that's going to give us this nice little rule, like dissolves like. The reason certain ionic compounds dissolve in water is because their intermolecular forces are close or similar to the hydrogen bonds going on between water. Now, the trends are much more predictable. Polar molecules typically do mix with polar molecules, and nonpolar molecules only mix with nonpolar molecules. And typically they don't overlap too often. Polar and nonpolar do not mix too well, and ionic and nonpolar do not mix too well. Alright. I have no idea why I have that picture anymore. Alright, how about this? Which of these do we think would be insoluble in water, or would actually be a solid if we add it to water? Alright, so we have a couple of substances with sodium in there. And if we remember correctly, sodium salts were pretty much always soluble in water. So I'm going to put X's on those. Those can't be right. And the other two are ones we may have heard about. D is probably not one you've heard about in this class, but naphthalene is something that's around. But acetic acid we have. This is vinegar. And vinegar must be soluble in water because that's how we buy it. Vinegar is added to water. That's what vinegar-based salad dressings look like. So it must be this naphthalene. Now give it away that it's actually likely to be in soluble water, and that it's nothing but carbons and hydrogens. Most hydrocarbons are going to be insoluble in water because they're just nothing but CHs. Those are pretty much guaranteed to be nonpolar molecules, and therefore London dispersion forces only. All right. Next thing we're going to talk about is some of the math that we're going to do. We're going to introduce at first our concentration terms. Fortunately, there's only two that we cover this early into chemistry. Only one really gets used in the lab too much, and that's the second one. That's this molarity, and its units, I'm going to expand on it right now, is the moles of the solute over liters of solution. Now, reason that molarity is much more common is because we like to deal in terms of moles. And this would get us closer to that. Only one of the units would have to go away, which would be the volume. All right, the other one, the percent composition, really is a percent. So if you ever see a label that says like 30% isopropyl alcohol, now that does mean 30% isopropyl. But more specifically now, it means that there's 30 grams of isopropyl to every 100 grams of solution. Or we could have said 70 grams of water in this case. But if you see just a percent on a label anywhere, it must be grams over grams. Even if it's a solution, it is still by law now required to be a mass percent unless it says otherwise. And you do see some of them otherwise. Sometimes you'll see a 30% and they'll put in parentheses V over V. That does mean volume over volume, which really means you do it in liters over liters or milliliters over milliliters. It's just whatever it is, you leave the units the same, just use a volume unit. But since these are mass percents, we're going to use grams. Theoretically, we could use kilograms, but they just need to be the same unit on both. Alright, so what does that mean? Like, let's look at this example. We have a solution of H2S in H2O is prepared by bubbling H2S gas into the water. Calculate the concentration as a percent by mass, given there's 0.29 grams of H2S dissolved in 75 grams of H2O. Now, I know a lot of us are going to want to take that 0.29 and just divide it by the 75. But if this is a percent by mass, the bottom needs to be the mass of everything. So I need to add those two together. This can be a very small number. 0.29 divided by 75.29, and then times 100. 0.385%. All right. Molarity, the more common one, at least for the chemistry labs, is moles of solute over liters of solution. Now, it will be typically written something more like this on like a label that says 2 molar, and that means, we can expand it, there is, and it does say sugar, so 2 moles of sugar to every liter of solution. All right, let's do one of these with an actual set of numbers. All right, calculate the molarity of a solution prepared by dissolving 2.8 grams of solid sodium chloride in enough water to make 135 milliliters. All right, it's the molarity. So I'm going to start with those grams of sodium chloride, and I need to turn it into moles. That would give me moles. And to get molarity, moles per liter, divide this by the volume I'm going to make, which is 0.135 liters. Just moving the decimal there. And what do we get? So 2.8 divided by 58.44, and then divide that by 0.135, and we get a molarity of 0.355 m. Okay, next, how do we actually go about making these? Well, in the chemistry lab, we have a actually very specialized bottle. Bottles shaped like this, they actually call them volumetric flasks. They will always have just a single line on them. Like if this, for instance, is a 1 liter volumetric flask, we can guarantee that's 1,000.00 milliliters. That's how accurate they typically have those lines. You get a set of these out and look at them, all of the lines are going to be on a slightly different level because somebody that's their job. They sat in a lab, all they do all the time is calibrate these little volumetric flasks. Alright, but what you would do, and the reason they are shaped like this is kind of interesting. So we have a known amount that we want to dissolve in that liter. So this is weighed out in mass, but we know how many moles there is, so we can make that molarity of solution. And we're just going to add some distilled water to it. Now we don't fill it completely. In picture B, they're showing it filled halfway. Now really is, so you can grab hold of this by the neck up here and swirl it around. And you can swirl it fairly violently, and you don't have to worry about it splashing up and coming out of the solution. That is why they're shaped this way. Got that long handle. And even if this gets hot, glass does not do a very good job of transferring heat, so it won't necessarily be hot up here. So you'll stir that. Once that solid is totally dissolved, then you fill it up the rest of the way to the line. Put a lid on it, invert it a couple times, and you've now made a solution. Okay, so in the stockroom, we typically have certain substances that come as solutions that come in stock concentrated values. So concentrate is typically how we get our acids. For instance, hydrochloric acid, which is one of our strong ones, it's in its own special cabinet in a stock room. It actually comes in containers that says 12.1 molar concentration. Now, I never let students actually touch that stuff. I don't even really let the TAs touch it. We dilute that before we get to use it, and that's what this is talking about in the diluted form. But the solutions we buy, we typically buy them as concentrated as we're allowed to, and then we do the dilutions to make them into stuff that we want. And we typically just dilute it once. So if I want to make 1 molar, I dilute the 12.1 just the right away. So I do it in one nice little step. But how we do the dilutions is kind of interesting because we actually can just use this one single formula. MV equals MV. Molarity times volume equals molarity times volume. Like I just said, I wanted to make some 1 molar solution from that 12.1 molar solution. Well, what I need to know is, well, how much do I want to make? Let's say I want to make 500 milliliters of it. Well, if that's the case, I could actually guarantee that here's what I could do. I could take that 1 times 500 and then divide that by 12.1. What that just told me is that I need 41.3 milliliters of that stock solution. So I need a very small amount. I'm going to put it in a volumetric flask like we just had on that previous page, a 500 milliliter volumetric flask, and then fill it up to 500 with just water. Now, typically, so I'm going to back up to the picture. So we're saying there's going to be 41 milliliters of hydrochloric into this 500 milliliter flask, and then we're going to add water to it. You typically want to add the acid because you don't typically add water to concentrated acid because it'll splatter and do stuff. So what I would probably have done is put about half full of water, then added my 41 milliliters of hydrochloric, and then filled it up to the line with water. Alright, let's see if we can do this with a different one. This is one that doesn't get hot and not really dangerous. This is just methanol. So we want to know what would be the concentration that we'd obtain if we were to take 25 milliliters of a 2.04 molar solution and dilute it to 500 milliliters. Alright, so my first concentration, 2.04. My first volume is 25.0 milliliters. We're going to solve for our second concentration. And the volume here, we got to watch out. Sometimes it might say going to dilute with 500 milliliters, but it's saying diluting at 2. So our final volume is 500 milliliters. That's 500.0. Oops. So 2.04 times 25 and then divide by 500 gives us a new concentration of methanol of 0.102 molar. Matter of fact, if we were going to put that onto a label for our chemistry lab, we would probably write 0.0102 molar, and then we'd actually say what it actually is. And then, if this is a full label, going to put our initial so everybody knows who made it, and then I'll date it. Let's see. This is close enough to August. Alright, next thing, another little dilution here. Let's see if we can do this one on our own. So pause it, take a moment, see if you can figure this one out on your own. Alright, so we want to make a 2 molar solution. We don't know what volume we want, but we want to make from it 0.1 molar, and we want 100 milliliters of it. So 0.1 times 100 divided by 2 is 5, and it'd be milliliters. Alright, now this formula, MV equals MV, actually works for concentrations as well. So if I'd given you 50% solution, we could use 50% solution and whatever that, but the units would have to be the same. We would have both concentration units be mass percents, or they're both molarity, and this equation would work. Alright, next little thing. Stoichiometry just relates how we're going to relate the molarities and such, and sometimes the mass percents to balanced equations. So we're going to be adding to what we've already done, which is our basic strategy for calculating moles and such. We're just going to add the possibility of converting from moles, or converting to moles from that concentration. Going to end up looking something like this. Alright, first things first, that should be an arrow. That's okay though. Alright, so we want to calculate the mass of solid NaCl that must be added to 1.5 liters of 0.1 molar silver nitrate in order to precipitate every bit of the silver ions. Alright, so what we want, so we're mixing these two together, we want to know how many moles of silver we're dealing with. So the very first thing I'm going to do is take that 1.5 liters of the 0.1 molar, and I'm going to rewrite this as moles of AgNO3 per liter. Alright, now technically that math's going to give me moles of just silver. Well, that's okay, because what I want to do is actually relate that, and I'm just going to write it out here. This isn't really telling me anything useful, but I wanted to write out how much it is. Now, that's not going to help us necessarily. I just wanted to put in there that that's silver ions, which is what it's asking about. But technically, we want to see from our balanced equation, for every AgNO3, we would need 1 NaCl, because that's how our balanced equation shows it. So I'm not going to use that at all. That is telling me how many silver ions in there, but I really want to see that this 1-to-1 ratio is what we're looking for, because that's how we're going to make all the silver precipitate out. Alright, and if I do know that that's the relationship between moles of silver nitrate and moles of sodium chloride, I can convert my moles of sodium chloride into a mass with the molecular weight of sodium chloride. .44 grams. Alright, and our calculation altogether is going to look something like so. So I take the 1.5 times the 0.1. That's my moles of silver nitrate and my moles of sodium chloride that will be necessary. And we're going to multiply that by 58.44. And we get that we need a mere 8.77 grams. Alright, one more of these just to see some more practice. So we want to know what volume of a 0.2081 molar potassium iodide solution is needed to react with 43.8 milliliters of a 0.3842 molar solution. Alright, we're going to start with these two because we know both aspects. We have a concentration and a volume for one substance. So I'm going to start by changing the 43 into 0.4388 liters. And I do that because this is moles per liter. 0.3842 moles of copper nitrate per liter. And I know the relationship between our copper nitrate and the potassium iodide that we care about. Alright, now, technically, moles cancel and liters cancel. So all this math here would give me moles of potassium iodide. We actually want volume. So we're going to take this molarity and invert it, because that's now moles of potassium iodide per liter. Now the moles cancel. If we go straight across there, we'll be left with the liters of the potassium iodide solution we want. So 0.04388 times 0.3842 times 4 divided by 2 divided by 0.2089. Now this is a volume in liters. My question asked for milliliters, so milliliters wise, this is 161 milliliters. All right, there's plenty of other practice problems in your book, and you have some worksheets to work on this. So be sure to hit me with some questions if you have any.